Hi, I'm Christopher Chapin, and the topic for my project and literature review was applications of new FPGA technologies in modern embedded systems. First, a bit of introduction to my topic. This presentation will run down some of the key points from my paper, with the paper obviously delving much more in depth. The general idea here is that advances in FPGA technologies has allowed them to become a viable solution in many embedded systems. And with technology scaling and Moore's law, the fabrication of ASICs has become more expensive, leading to developers considering FPGAs as a cheaper, more flexible solution in many embedded applications. A trend I saw over and over again in my research for my paper. And first, a bit about the presentation layout. First, just a brief overview on FPGA technology, then a review of some of the modern day advancements in FPGAs that allow for application in embedded systems. And finally, some trends and examples of FPGAs used in modern embedded systems. And so first, to kind of go over a general overview of FPGA technology. At its core, an FPGA is composed of lookup tables, flip-flops, and a routing matrix. And the lookup table essentially acts like an electronic truth table, storing the values of any Boolean function that you want to implement on the FPGA. And so by substituting the actual logic gates of some digital circuit you're trying to simulate with this lookup table, while slower, it allows you a greater degree of flexibility and the ability to mimic the function of any digital circuit using an FPGA. And so these lookup tables and flip-flops are packaged into slices and complex logic blocks and then connected to a global routing matrix to kind of make or break connections as needed on the chip. And next, kind of looking at some of the general comparisons between FPGAs and ASICs that I did for my paper. And so the key points to take away from that were that it was found FPGAs on average were about 20 times larger than ASICs on chip, about 3 to 4 times slower when comparing critical path delay, and about having 9 times greater dynamic power consumption compared to ASICs. And so look at these metrics, it kind of makes the FPGA solution look pretty bad, and you would wonder why I use one. And again, the answer lies in it's a cheaper, easier solution today than going and fabricating a new ASIC, for example. Flexibility is very desirable in embedded systems today, which FPGAs certainly provide. And as you'll see in the next slides, advancements in FPGA technology are certainly helping to bridge this performance gap. So one of the first big advancements I looked at was integrating hard components onto an FPGA chip. And so this would be things like actual memory blocks or digital signal processors, floating point units, and hand off hard computational tasks to these processors that they're specialized in, and therefore freeing up FPGA resources for simpler tasks that they can perform better at. And doing so, it was found provided great benefits in terms of performance increases and reductions in power consumption. And with technology scaling, this has become very popular and commonplace in FPGAs today to include many of these components on chip. That kind of leads into the next advancement, which is a combination of hard processors with FPGA fabric, either integrated directly on one system on chip, or in some cases just kind of combined into one system. And so one interesting example I saw from my paper was this team of researchers went and combined a dual-core ARM processor with a Zinc 7020 FPGA device. And by doing so, they actually use the ARM cores to, first of all, run software tasks and also manage a mini-core system running on the FPGA side. And another very interesting point they raised by doing this was it allows for flexible hardware-software partitioning, where you can move tasks between the two as you see fit, which I know in embedded systems today, specifically, that partitioning problem is very difficult, for example, as we've covered in class. So doing something like this allows you, even after design time, to kind of switch tasks back and forth. And so next I looked at the implementation of many core systems onto an FPGA. And one example of that could be the one from the last slide. Another very popular cheap alternative today is simply using an array of soft core processors using the FPGA fabric. And many of these soft core processors are actually provided by FPGA manufacturers or just as open source projects. And here on the slide, you can see a table with some of the more popular soft processors today. Microblaze, for example, Xilinx is one they include with their boards. And some of these other ones are very popular open source alternatives. And so on the next slide, looking at and kind of comparing the architectures between Microblaze and Leon 3. In general, the soft core processors had pretty shallow pipelines and low clock frequencies, which you'd expect is kind of a limitation of the FPGA hardware and architecture. And then comparing the execution times running on a benchmark between the Microblaze and the Leon 3. Overall, the Microblaze was the fastest of the soft core processors that were looked at, with the Leon 3 being pretty close in terms of execution time and performance metrics, and offering a good open source alternative to a Microblaze. Next, I looked at some embedded network on chip strategies for an FPGA, and the idea here is replacing the routing matrix, which you would normally use as your interconnects on chip, which is not very optimized and pretty power hungry, with an integrated optimized network on chip architecture. And so this specific example from my paper I looked at used a mesh topology on a 28 nanometer FPGA, and it used 64-bit addressing, 1067 megahertz clock on network, and achieved around 22.5 gigabyte per second bandwidth. And additionally, I had a few different innovations for interacting with the FPGA fabric called Fabric Port and IO Link. The details of those are in my paper. And next in optimization I looked at was actually on the software side, and specifically in optimizing software to improve hardware synthesis for the FPGA. And one thing I looked at was an improved packing and placing scheme called Ripple FPGA, where the packing and placement of core logic blocks during hardware synthesis was kind of done at the same time instead of in two steps, which is kind of conventional to do today. And by doing those at the same time, they managed to achieve a 5.5 times speed up over conventional synthesis methods. The idea being by doing them at the same time, one kind of optimizes the other and allows you to pack and place more optimally. And then next, I looked at some optimizations to some high-level synthesis languages and found that they had a big determining factor on the overall speed of the FPGA after compilation. And so for this, I looked at 6 different HLSs in a research paper, and the conclusion was being that OpenCL using Intel's SDK kit was much faster than the rest. As you can see on the next slide here, with the yellow lines being the unoptimized and optimized OpenCL language. So kind of the takeaway here was that software optimizations, as I said, can perform and can provide huge speed ups in terms of FPGA performance, and so shouldn't be neglected when considering optimization of the overall system. And then finally, an interesting optimization I looked at was in optimizing FPGA boot up and synthesis times, and this is kind of specific for embedded systems, where that might require some very strict timing deadlines and tasks being done at startup. And so today, typically FPGA boot ups are too slow to deal with a lot of these system requirements. As you can see from my diagram, the FPGA is considerably slower due to the time needed for hardware configuration compared to, say, an ASIC. And so an interesting optimization that was done here was on using a new scheme called fast configuration to essentially compile the parts of hardware required to handle any tasks needed immediately at startup to meet these critical deadlines. and then from there use dynamic partial reconfigurability to continue configuring the rest of the hardware after those tasks have been completed before deadline. And so this was a very interesting idea I saw in a research paper, and kind of allows FPGAs to be used in a lot of these embedded applications with these strict deadlines where otherwise they would be too slow at startup to be used. And so for the next big topic was FPGAs in modern embedded applications. And first, a couple general trends in that market I saw. High performance computing applications is very important in embedded systems today. That includes things like parallelization, flexible I/O ports, and overall flexible functionality, of which FPGAs excel at all these. And so they're in the market today in many situations. One specific example I looked at was FPGAs in aerospace. And here I saw FPGA manufacturers working very closely with the aerospace industry to meet their strict regulations, such as DO 254 was one I saw and looked into. And so features that have been added to kind of meet these regulations include things such as single event upset tolerancy, triple modular redundancy, and Xilinx recently came out with their newest boards have dynamic redundancy, thanks to the FPGA's programmable logic and advanced bit error correction. And then following from that, another kind of very unique, interesting application in an embedded system that I found through my research was actually implementation of a fuzzy logic microcontroller on an FPGA board. And so I kind of delved into the topic of fuzzy logic, which a full explanation exceeds the scope of the presentation in my paper. But essentially, fuzzy logic controllers allow for flexible, smart, adaptable control systems in embedded devices and are widely used today. And the key idea is that flexibility of hardware and software partitioning is desirable for fuzzy logic systems. So for this specific example, implemented a fuzzy logic controller on a Spartan 3 FPGA kind of as a proof of concept. And a software tool called XFuzzy was used to synthesize the required fuzzy logic FPGA. And on this next slide, you can see the software hardware partitioning. Like I said, the flexibility there is very important. And on the right, you can see kind of a complicated flowchart detailing using the XFuzzy software tool to kind of compile the required fuzzy logic into VHDL description language, and from there send it to the FPGA for hardware synthesis. And so that kind of takes me to a conclusion and a summary of the main points I discussed. The big idea here to keep in mind is that FPGA advancements covered in this presentation have played a big role from what I've seen in their increased use in embedded systems today. The trends that I covered and the examples show that they've already had quite a bit of market penetration. And kind of an interesting overall trend for FPGA technology I've seen in my research is that initially they were just kind of a curiosity in the 80s at their conception, and then were initially only used for things such as simulation and specification of quote-unquote real circuits like a ASIC or a general purpose processor. And now today are a much more viable permanent solution in many embedded products. And